Hi everyone, it's with great pleasure that I present our work, A Unifying Information-Theoretic Perspective on Evaluating Generative Models for AAAI 2025. I'm Alexis Fox from Duke University. I also want to acknowledge my mentors and co-authors, Dr. Swarup and Dr. Attica from UVA's Biocomplexity Institute. We start with the motivation behind our work, which is that assessing generative model output is non-trivial, as generative models produce a spectrum of plausible outputs based on the learned data distribution. Therefore, creating a meaningful automatic metric is difficult. Some of the more traditional popular metrics include Frechet inception distance and inception score, which have seen success, but they come with a few issues, namely that they can't distinguish between different failure modes, such as when outputs are generated in low probability regions of the real distribution, i.e. low fidelity, or they insufficiently represent high probability regions, i.e. low diversity. Also, these metrics can't be dissected for sample level analysis and are mainly used for distribution level comparisons. Starting with work from Sajati et al. In 2018, who repurposed the terms precision and recall from the classification domain to describe measures of fidelity and diversity respectively, multiple k-nearest neighbor-based metrics have been proposed to quantify the fidelity to diversity trade-off. While the multidimensionality of the metric allows them to distinguish two failure modes, we note an issue with the diversity component. Specifically, there's often an overemphasis on interclass diversity, as it is easier to diagnose, and consequently an underemphasis on interclass diversity, despite parameters that control the fidelity diversity trade-off, like classifier-free guidance and temperature, exhibit variance in interclass diversity. Another issue is that many of these metrics only provide empirical definitions, without clear theoretical forms, which makes their interpretation more ambiguous. Both of these issues we seek to alleviate through our work. To explicate the different failure modes, here we visualize three different ways a model output can be considered suboptimal: mode dropping, mode invention, and mode shrinkage. In this figure, the real, i.e. green distribution is composed of two modes, pickup trucks and sports car. The pink is the generated distribution. Mode dropping, A, represents one type of recall diversity loss, where the model lacks sufficient coverage of certain real regions, which in this case is pickup trucks. Mode invention indicates a loss of precision, i.e. fidelity, occurring when the model generates implausible outputs that do not align with the real distribution, as seen by these samples. Mode shrinkage happens when a model repeatedly produces highly similar points, lacking intra-class diversity, that represent a sort of mode average, here highly similar red cars. Here we introduce brief background concepts for our work, specifically revolving around information theory. Here we let calligraphic x be a random variable with distribution f sub x, and we let x be a set of nx samples. We let fx and fy represent two general distributions, and we let fr and fg represent the real and generated distributions respectively. We also define three relevant information theoretic terms, namely entropy, cross-entropy, and KL divergence. Considering practical applications, we use K&N-based estimators of information theoretic terms for both our metrics empirical form and our unifying perspective for other metrics. We highlight one such estimator for cross-entropy, and note that estimators for other terms follow similar logic, namely that K&N distances can be used as a proxy for probability density. We also note that the ratio of points within a K&N ball can also be used as an estimator. Intuition for the estimator of cross-entropy is highlighted in this video, specifically emphasizing how the estimate of cross-entropy between the generated and real distribution can be a useful fidelity measure. This is a GUI we made to demonstrate this point. Here, the green points represent real samples. We set k is equal to 2. We now add pink points, which represent generated data. Note how the average distance between the generated and real points, as well as the cross-entropy, changes, specifically when adding implausible generated points, which increases both terms considerably. We also select certain points and visualize the second nearest neighbor distance, highlighting how cross-entropy estimators can be used for sample level analysis. And through the hypersphere visualization toggle, we also briefly showcase the potential of the point ratio within the balls to also estimate density ratios. One of our contributions is integrating existing metrics into an information theoretic framework, allowing for easier interpretation and motivation for our metric, which we talk about in the next slide. We utilize the K&N ballpoint ratio method from Noshat et al., alluded to earlier for our derivations, with more details in the paper. We integrate two metrics, precision coverage and recall coverage constituting one, and density and coverage constituting another. Both metrics aim to quantify fidelity and diversity separately. We derive theoretical forms for all. And note they estimate the general divergence form of the divergence of x from y equal to the expected value of values drawn from x of the function g of the probability density ratio fy over fx. Here, we highlight that the divergence of G from R is the suboptimal form for measuring fidelity, as it unfairly punishes dense generated samples because of the FG term in the denominator. We first note that the KL divergence of G from R is equal to the cross entropy of G from R minus the entropy of G. We substantiate our earlier claim by comparing the closed form expression for all three terms when increasing the variance of the generated distribution. Precision measures in this scenario should observe decreased fidelity, as G increases its variance relative to that of R. However, we observe the KL divergence values at variance 0.25 and 2.5 are approximately symmetric around the variance equals 1 case, illustrating how both underestimation and overestimation of variance relative to the true model contribute comparably to the divergence, which is suboptimal as the motivation of multidimensional metrics is to distinguish these cases. We highlight that the basis of R metric in the next slide, cross entropy of G from R, trends in the right direction. We leverage the asymmetric nature of cross entropy to construct an information-theoretic interpretation of precision and recall. R metric has three components, or measures, as seen here. Precision cross entropy is our first component, which is equal to the cross entropy of the generated distribution from the real distribution, minus the entropy of the real distribution, which serves as a constant baseline. Precision cross entropy measures fidelity, and is minimized when generated points are in high probability regions of the real distribution. Our second component is recall cross entropy, which is defined symmetrically for the cross entropy component, and it measures interclass diversity, and is minimized when high probability regions of the real distribution are densely populated by generated samples. Our last component is recall entropy, which is equal to the entropy of the generated distribution minus the entropy of the real distribution, and it measures interclass diversity. The more similar generated points are to each other, the lower recall entropy is. Now we highlight experimental results, which support our metrics' alignment with desired properties. Our first experiment is with human judgment correlation for fidelity. Although there is no clear ground truth for overall assessment of generative output, human assessment has been used as a ground truth for realism component of metrics. For this experiment, we measure the Pearson correlation between various fidelity measures and human judgment error rate on the Cypher10 and ImageNet datasets. We note that precision cross entropy, our measure, precision coverage, and Frechet distance have similar positive correlation with human error rate for both datasets. However, density, the measure, shows undesirable behavior, namely negative correlation on the Cypher10 dataset, while a positive correlation on the ImageNet dataset, which shows an inconsistency that is undesirable for grading. Our next experiment is mode dropping for interclass diversity. To assess mode dropping sensitivity, we drop 100 random classes at a time from an ImageNet ADMG ADMU generated dataset. For clarity, arrows are put aside each measure's lines. Upright arrows mean that higher values indicate better fidelity or diversity, and the opposite is true for downward arrows. Mode dropping measures, coverage, recall coverage, or measure recall cross entropy should show significant change in this experiment, while precision and mode shrinkage measures, density, precision coverage, precision cross entropy, and recall entropy should remain relatively constant, and in this experiment, all perform as expected. This experiment is mode shrinkage for intraclass diversity. For the experiment, we calculate the metrics for image sets generated at 5 levels of the classifier-free guidance parameter, which is used to control the fidelity-diversity trade-off. With increasing classifier-free guidance, fidelity increases and interclass diversity of the output decreases, and the measure should reflect that. Precision cross entropy and density perform as expected. However, precision coverage decreases for higher classifier-free guidance values, which is suboptimal. Out of the recall measures, only our interclass diversity component recall entropy shows significant sensitivity to mode shrinkage. We conclude with our contributions, which are first, unifying existing metrics, precision coverage and recall coverage, and density and coverage. For these metrics, we provide information-theoretic derivations, which helps explain their empirical behavior and motivate our metric. On the topic of, we propose novel information-theoretic metric, precision cross-entropy, recall cross-entropy, and recall entropy, which separately measure fidelity, interclass diversity, and intraclass diversity, respectively. Our metric can be dissected for sample level analysis, unlike fresh eye distance or inception score, and uniquely separates diversity in two components, which helps emphasize the often overlooked component of intraclass diversity. Our experimental results provide empirical support for our metric's alignment with desiderata, such as significant correlation with human judgment.